Thanks for everyone here. Now I'd like to talk about the security of NVIDIA Tegra platform. Hope you can enjoy it. First, let me introduce myself. My name is Nie Sen. You can call me Sen, and I'm a security researcher at the King Security Lab of Tencent. It's also known as King Lab or King Team. I bet some people here already know us because of the pontoon, right? And I'm one of the researchers at King Lab who are focusing on the security of smart cars. So we do some car hacking stuff. For example, I hope you already know our showcase, the Tesla remote hacking. In September 2016 and in June 2017, we remotely hacked into the Tesla car without any physical access. We can control the car in both parking and driving mode. So you can find more information from these links. This is the agenda. Firstly, I'll talk about why we need to dig into the Tegra platform. Then I'll explain the details in the NVMap driver. We'd like to review some known vulnerabilities related to the Tegra platform and finally share some bugs found by ourselves in the NVMap module. So what is the NVIDIA Tegra platform? Tegra is NVIDIA's embedded Linux development platform. It is used in many types of devices, such as smartphones, game consoles, and of course, the automotive systems. I must say that Tegra is widely used in the embedded systems. Here I give three famous products. My favorite game console, the Nintendo Switch, and also my favorite ebook reader, the Kindle, and of course, Tesla uses Tegra as its infotainment systems. Also, BMW is using Tegra platform in their cars. So we can see that Tesla and NVIDIA, they are good friends. They are automotive partners. Based on the Tegra processors, the Tesla car has the advanced infotainment system and the IC system. So why we need to dig into the Tegra platform? We dig into it because of our Tesla hacking research. During our Tesla hacking research, we need a way to gain root on the Tesla infotainment system. That's an important part in our whole attack chain. So firstly, we already have a code execution bug in the browser context, but the browser process is running in the low privileged user ID, and it's also in the sandbox, the AppArmor sandbox. So we need a local privilege escalation vulnerability. And I think, so here I will give a demo video to show how we get the browser shell first without physical access. Then I'll explain why we need to do a local privilege escalation. Okay. So I'm not sure. Okay. So, firstly, we create our fake AP. And you can see we do not need to physically access the car, but the car will automatically connect to the fake AP. So need some seconds. And then you will see the browser. It will reload itself, reload the web page itself. Then we use the WebKit vulnerability to exploit it. From the videos frame, you can see that we got a shell. It's in the browser user ID. It's also in the AppArmor sandbox. Okay. Go back to my slides. So here, it's in the step 3 and step 4, we need a local privilege escalation. In the year 2016, we utilized a well-known kernel vulnerability. So it's easy. It's a well-known bug in the mainstream kernel, but not the kernel-specific part, not in the NVIDIA drivers. But however, in the year 2017, things become much more difficult for us because Tesla patched all the known vulnerabilities. We need to find a 0-day to hack into the system. So actually, before we dig into the Tegra platform, we use about 1 month to try to find a new vulnerability, but we failed. So we need to focus on the Tegra. As you can see, according to the AppArmor rules, the dev/nv map and the dev/nv host control is the only 2 drivers can be accessed in the AppArmor sandbox. So at that time, we decided to dig into the source code and try to find a bug. Here I will give a brief introduction about the nvmap driver first. But before we talk about nvmap, we need to talk about nv host control. It's a driver that it's the Tegra graphics host driver. And new people already found some interesting bugs in this module, so I'll talk about it later. But for me, I didn't find something new or something special in this module, so I quickly go over it and move to the nvmap module. So, in my mind, nvmap is much more complex than nv host control. What is the nvmap? nvmap is the memory manager for Tegra GPU. In the mobile phone or in the embedded systems, user process needs a way to communicate with the kernel and with the GPU, especially for the large chunk of memory sharing and memory read-write. So that's why Tegra creates its own memory management module in the Linux kernel. But it's very similar to Android mechanism. You can find some other similar implementations on the Android devices, such as the CMAM. CMAM is the memory manager in the TS-OMAP chipset. So something like that. And nvmap, actually, it's a typical Linux driver. A user process can access it by open the driver and get the handle to operate it. Then it can be sent some I/O codes. You can see the I/O codes there. There are many I/O control command codes. For example, the nvmap IOC create, alloc, free, mmap, and the last one, the pin multiple. I'll talk about them later. As a programmer, not as a hacker, as a programmer, how can we use the nvmap user interface? I think you should learn all the structures in the code base. For example, you can find those structures in the nvmap IO control head file. For example, the nvmap open. This function will create a pointer to the nvmap client structure, and the nvmap IO control create will create a nvmap handle structure. So it's the similar logic. You can find some other structures in the code base. And after we create and alloc the kernel memory buffer, there is a way to map the memory buffer into the user space. It works together with some syscalls like the map. For example, if you invoke the map syscall to hold a user space address, and then you can send the IO control commands via the nvmap user interface. It will map the nvmap memory buffers to the user space. So also nvmap is used to manage the memory. So there are different kind of memory pool that nvmap can handle. For example, it has different policies for different size of memory requirement. If the size is small, it's less than 1 page, it will prefer to allocate from the system heap, right? If the size is very large, it will use the large heap type. So I think it's very good for us. I will talk about it later. Here, we'll talk about how to allocate physically contiguous memory pages. I think in the code base, the nvmap heap carve out mask. This type of heap pool is a very good candidate. We can find some comments in the code base. It says that carve-outs are platform-defined regions of physically contiguous memory which are not managed by the OS. So it's perfect for us. We can have the physically contiguous memory. And if we want to allocate the uncached pages in the code, we found this function. And you can see here that since nvmap has its own cache management function, so absolutely, I think we can have the uncached pages. So it seems it's very good for us. The last I/O code, the nvmap IOC pin or on-pin multiple handles. This is a very important feature in the nvmap kernel module. It pins a list of nvmap handles and maps the corresponding memory pages into the IO VMM space. So in my viewpoint, this interface is used to communicate between the user space process and the GPU. But here you need to remember you cannot unpin the unallocated nvmap handle. If you do this, you will trigger the bug on function. So you cannot unpin it before it is allocated. Here we will review some known issues because as a bug hunter, we are familiar with the bug hunting routine. Firstly, we analyze all the known issues and find out the code patterns. Then we apply those patterns to the new code base and try to find the new vulnerabilities. That's why we will explain those vulnerabilities. These vulnerabilities are very typical and very interesting. I will talk them one by one. Like the first one. The first one, another Chinese security researcher named Peter P, who published this bug at HITB So from my viewpoint, this bug is very straightforward. From the picture we can see the num offsets and the block size, they are totally user controlled. But before the keymalloc is called, there is a lack of checks. So this is a typical heap overflow bug. Interestingly is that this bug can be directly exploited on the Tesla infotainment system. But it is absolutely fixed on the Tegra 3 platform. I think it's very bad news because someone found this vulnerability and he reported to Tesla. I think maybe they fixed all these kind of bugs. I cannot find the similar pattern in the NV host control. So I need to move on to the NV map module. Again, I must say that NV map is much more difficult than NV host control. The second one is also interesting. This bug, actually, it is related to NV map. If you want to exploit it, you need some tricks. Firstly, it's a race condition-based use after free bug. From the picture, we can see you need to successfully to duplicate the FD handle at point A. You need to duplicate it. And then at point B, you should give the copy to user function its destination to a read-only memory. Then it will trigger failure. And the FD handle's ref counter will be 1. Now you have an FD handle in the user space, which can be freed at any time you want. So you can exploit it in the future. If you want to know the whole details, you can find the tricks in the links below. Because it's in the NV map module, so we need to review it. But this bug is exploited in the Nexus 9, which is not the same code base with Tesla. Tesla is similar to the Nexus 7 phone, I think. So we found the function code here, and you can see from the picture, you can see the handle field. It's not a system file descriptor. Actually it's a structure pointer. So they are totally not the same logic in the Tesla infotainment system. We cannot, like here, I must say, the idea cannot be borrowed to Tesla hacking. We cannot find the same issue in the Tegra 3 code base. And then at that time, I came across to the famous vulnerability named Rowhammer or Drummer. The author of Drummer published the first root exploit, which can be used on the ARM Linux. It's a new attack that exploits the Rowhammer hardware vulnerability on Android devices like the Nexus 5. The big difference between Rowhammer and Drummer, or we can see the big difference between exploiting the Intel device and the ARM device is how to allocate the uncached physically contiguous memory and test the bit flip. So Drummer uses a very cool idea. It uses ARM interface in the mobile phone. In the Android phone, it uses ARM as its memory management. So I'm curious, is Drummer exploitable on the Tesla infotainment system on the Tegra platform? We have a key benefit. Remember, we have talked it earlier. NVMap can also be used to allocate the uncached physically contiguous memory. So it's a key benefit. Then I decided to have a try. So it's easy. I just wrote a kernel function and built it into the Nexus 7's kernel and tested the bit flip. But I tried lots of times, and but the bad news is that the bit cannot be flipped. So this bug is not work in the Tegra platform. After we reviewed all the known vulnerabilities, so we realized that we cannot easily exploit the Tesla kernel with a known vulnerability. So at that time, we need to find our own zero days, find our own vulnerabilities. To be honest, after we dig into the source code, I must say that the code quality of NVMap module is not very good. So we found some interesting bugs. Here I will introduce some infer-leak bugs of different types, like the first three bugs. Then in the end, I will talk about a bug, the CVE 2017-6261. This bug it's very good. We use it to root the Tesla infotainment system. Actually, it's not. It's more than enough. It's perfect in our Tesla hacking research. But first, we'll talk about those infer-leak bugs. The first one is the NVMap handle pointer infer-leak. Here I'll talk about it. Firstly, from the picture, you can see the user can invoke the L control with the command code nvmap IOC create. The nvmap driver will return a handle to the user space. It is a handle for the memory you will operate in the future, like you can alloc or free it. From the macro-defined function, we can see that it's not same as the bug found by Project Zero, right? It's actually it's a pointer from the ref structure. Here we will have a clear image that we can see the handle, the edge is KZ-alloc. From the KZ-alloc is a structure, and then it is assigned to the ref's handle field, and finally it will return to the user space, right? So it's a pattern in the kernel mode. You alloc a structure, and then you return the structure pointer to the user space. It absolutely is a security issue, right? From this picture, we can see that the handle actually is a pointer to the kernel heap. The user can create any nvmap handle at any time. It means that maybe in the future, we can use this trick to predict the heap layout, or we can do the heap spree, right? So from this picture, you can see the handle, you can create it. And the second one is another type of infer-leak bugs. This bug is also very interesting, but it works in the earlier version of Tesla kernel. In the version maybe 2.6, there is no demessage restriction. A low privileged user process can also read the demessage output. And the second is that bug on function just write the ops message to the syslog and let the user process to die. So that we can imagine a scenario and which is really happens. Firstly, we will trigger a mini bug in the dev/nvmap. We already found one. Is that if we unpin the handle which is not allocated before, it will trigger the bug on function, and the bug on will print out the registers and the stack trace to the syslog. From the user space, we can read the demessage outside inside the AppArmor context. It means even we are in the AppArmor sandbox, we can read some sensitive information. From this picture, we can see that this is a bug triggered in the nvmap L control. And in the user space, we can read lots of kernel address information, right? So it's very useful when you debug your kernel exploit. I like it very much. And this is another infer-leak bug. It's a common mistake in the memory management implementation. It's like when user-land program requires memory allocation via nvmap interface, nvmap doesn't clean its dirty pages, so that we can request a large chunk of memory and search for the sensitive information in the allocated memory. Let's look at how to get the leaked memory information. Firstly, as always, we need to open the nvmap driver first, and then request a handle to operate the memory, and it can be invoked by the I/O control syscall with the nvmap create I/O code. Secondly, we can send the I/O code, the nvmap IOC alloc, and ask the nvmap to alloc the memory pages. Finally, this is an important step. You should call the memmap syscall first to get a virtual address in the user space, and then send the I/O code memmap I/O code with the address info. From the picture, you can see we use the retain value to send the I/O control syscall. So now you can read the memory out from the user space address, the ADDR variable. So what we can see from the memory, here we have a demonstration image. You can, if we search for some kernel pointers, like it starts with the C1, and we can find something very interesting, right? So many kernel pointers in the memory. And okay, so this is the third infra-leak bugs. Here I will give a brief summary. Like the first bug can just can leak a pointer to a kernel structure, but the second bug can leak a panic context, which includes all the register information and the stack trace. But this bug, the last one, we can leak even more than 200 megabytes memory. It's not just the kernel memory. Because of the memory management, I think we can also leak some inter-process information, right? I think if at a good time, maybe we can get some token in the Tesla to directly route into the system, but I do not have this kind of luck. This is another vulnerability. This vulnerability is what we reported to Tesla. It can be used to gain root on the Tesla infotainment system. Actually, it's an arbitrary address decrement in the dev/nvmap drive module. So let's look at the root cause of this bug. And firstly, it's normal that a user process open the nvmap driver and invoke the I/O control syscall with the nvmap IOC pin multiple I/O code. You can also find the structure here. Right? We used this structure is what we used to send the I/O code from the user space. There is an array of handles. Because the interface is used to pin an array of nvmap handles. So here in the for loop, it will validate all the handles first in the array, right? If the nvmap validate get, this function get filled, the loop will be quitted. But the loop condition is very strange, right? The loop condition is wrong. When the variable write is not false, it will quit the loop. But before that, the index, the variable I, the increment step is already executed. It means that the value of I is already equal to 1 at this time. Even the first handle in the array is wrong. So let's see what is the next. So we can see that the value of I is assigned to the variable nr, so that we can enter another for loop. When we enter the for loop here, the first handle, the h, when I is equal to 0, the handle in the array is passed into the nvmap handle put function. Let's look at the nvmap handle put function. Nvmap handle put, this function is used to decrease the reference count. When the ref count is 0, the handle will be freed. But the address of the handle is totally user controlled. We can go back, like here, we can find that the NV mapping handle, this structure is totally user controlled. We can assign arbitrary value to the handles. So here we can decrease by 1 in the arbitrary address, which I think this is awesome. You can see the automatic return. At this time, the ref field will be decreased by 1. I think this is the root cause of this vulnerability. Actually, it's a arbitrary address decrement vulnerability. And so here is a code snippet. There is code to trigger this kind of vulnerability from the user space. You can see it's very, very easy. You can assign the address you want to decrease in the handles. Then we'll talk about how to exploit this bug in the sandbox, in the Qt car browser context. Here we need to handle 2 kind of different kernel versions, but the 2.6 is easy for us. But the Tesla has upgraded its kernel from 2.6 to the 4.4. So in the new kernel, we need to deal with some new mitigations. Here you can see those new mitigations. The first one is the PAN emulation mitigation, which means you cannot redirect the IP address to the PC address to the user space. You need to finish your exploit shellcode in the kernel mode. And the second one is the demessage restriction. We mentioned earlier, the demessage restriction is by default on in the new kernel. So we cannot read the demessage message out. So it seems we need to blindly exploit this bug. And the last one is the temp folder. The temp folder is non-executable, which means you cannot build your exploit in a standalone binary and drop it into the temp folder, which is typical in our exploit writing. But now we cannot build it into a standalone binary. We need to use something like full ROP tricks to do this kind of stuff. So in conclusion, if you want to exploit this bug, you need to write your exploit in like a pure ROP gadgets in the kernel mode. Then here we'll talk about how to bypass those kind of mitigations. For the PAN mitigation, actually, it's very funny at that time, I think, because the kernel is by default enabled this kind of mitigation, but we found that the text segment, the kernel code segment in the code segment in the kernel is still writable. What does it mean? It means that we can also use some typical Linux kernel exploit trick, like we can patch the kernel first and like modify the logic of this set RES UID function to easily set RES UID. This function with the argument parameter argument 0 to get root. So it seems this mitigation is useless in the new kernel. And here we'll talk about how to disable the demessage restriction. In the new kernel, there is a global variable named demessage restrict. From this picture, we can see this variable. The value 1 means enable and 0 means disable. So we need to change the value from 1 to 0. And it fits our bug very well because, this bug, we have the bug, it's a arbitrary address decrement by 1, right? We can easily achieve this goal. And at that time, there is no ASLR in the new kernel. So we can use this trick first to bypass the demessage restriction. And then we can use the demessage output to debug our exploit. It saves lots of time, actually. And for how to disable the app armor restriction, this one is a little difficult for us because it's different from the last slide, the demessage restriction, because in the app armor context, so we need to change the value from the app armor enforce to the app armor complain, which means we need to change the value from 0 to 1, which this is an increment operation other than the decrement operation, because we need to add 1 to the 0 becomes 1. So we need transfer our bug to another way, like we need a way to change the logic to an arbitrary read and write. So here, finally, we found I think it's a perfect way to make the bug into a code execution first. So we found a syscall named sysexcept4 in the syscall table. It's an entry in the syscall table, and it's rarely used in the Linux kernel, so it's very safe to modify it. And by trigger our bug multiple times, we decreased by 1 by multiple times. The entry address of this syscall will be, from the picture you can see, it can point to the BLXR3. So it's a jump. It's a jump to a register. And for syscall, you can control so many registers, like the R3 register, right? So if we assign a useful address to the R3 register, like the RP gadgets here, you can find that this is a read and write gadgets. We can make the code execution again to a kernel read and write bug. So till here, exploit this bug becomes very clear. We can make the decrement to a code execution, then to a arbitrary kernel memory read and write. So here we can see we can trigger our bug multiple times to modify it. We can trigger it multiple times. Then the sysexcept4 will point to a jump to the R3 register, right? And then, because now we have the ability to arbitrarily read and write the kernel memory, so we use the write gadget to patch the set RES UID function. It's a typical trick in the Linux kernel exploit. So by calling the set RES UID with 0 in the user space, we can get our root shell. And from this picture, you can find that we already exploit this infotainment, and we got a shell with the UID equal to root equal to 0, right? So this is our goal. And here in the end, I should give a special thanks to this paper. Actually, when I dig into the Tegra platform, we read this paper, the Android Iron Hazard, which is published on the CCIS conference in the year 2016. As I said, NVMap is very similar to the Android Iron mechanism, so that this bug pattern in the iron can also be used in the NVMap module. So I borrowed some ideas from this paper, and I like it very much. You can have a look. Okay, in the end, during the research, my teammate Liu Ling, he finished the final exploit. Because the bug is not complex, but we only have a very short term to finish our work. we need to use the full ROP tricks to finish the exploit in the Qt car browser. It's a totally blindly exploit. So my teammate Liu Ling is very good at the exploit writing. So he finished the work. And also my colleague named Jia Hong, who is very good at the Android kernel exploit. Actually, I think so many famous Linux kernel exploit is written by him. So at that time, we only have experience in how to disable the SE in Linux, but we are not familiar with the app armor tricks. So he told me how to bypass the app armor restriction in the kernel mode, and also some other car hacking researchers in our team. Okay, that's all. Thank you.